and he's going to talk about the Python visualization landscape. Give a hand to him. Thank you very much.
All right, thanks very much. Thanks for coming, and for many of you listening to me a second time in a couple days. I'm going to talk about Python's visualization landscape. And so back in, the fall, I wrote this abstract and said, I'm going to give an overview of the landscape of dataviz tools in Python. And then, a month or so ago, I thought, I should figure out what that is, right? So as I usually do, I tweeted and said, hey, these are the tools that I'm thinking of talking about. Are there any others I should consider? And Twitter came back with this whole thing. So, totally changed what I was going to do for my talk. But I want to take this time to make sense of this deluge of visualization tools that are out there in the Python world. There's tons out there, as you'll see. And I think each one is kind of specialized for its own unique application or its only unique strengths. And I'm hoping what each of you will take away from here is the ability to look out there and say, given my problem that I want to do, my visualization task, I know what package I should use in Python. So let's get started. It all starts with Matplotlib, right? Matplotlib has been around for over a decade now, almost 2 decades now, and it's kind of the core tool. And there's lots of things that have been built around Matplotlib. There's this base map CartoPy thing for geographical visualization. Pandas and Seaborn have some tie-ins to Matplotlib. We have things like ggpy, which gives a ggplot interface on top of Matplotlib. NetworkX gives you network visualizations. Yellowbrick and scikit-plot, these are some things that I learned about that do visualization for machine learning. So this is kind of like the Matplotlib cluster of tools that I think of, and I'll go into some of these a little bit later. On top of that, you have JavaScript. And in the last few years, a lot of these Python libraries have started to depend on JavaScript and use JavaScript to get some great interactive visualization. And probably the 2 biggest of those are Plotly and Bokeh. And you can, I'll talk about each of those later. But there are more. There's this toyplot and bqplot, which you may not have heard of, but they're really fun libraries to try out. And you have things that are tied to the Jupyter Notebook, like IPyVolume, IPyLeaflet, Py3.js. They let you take advantage of different aspects of JavaScript to do interactive visualization in the notebook, which is pretty cool. So there's other things. Cufflinks is built on top of Plotly. So that's kind of like the JavaScript cluster of visualization tools. And of course, there's more, right? You want to link JavaScript and Matplotlib. So there's this D3.js is a thing, and I wrote a package called MPL-D3 that links Matplotlib and D3. It's not super well supported anymore, but it's kind of a fun thing if you want to turn your Matplotlib plots into D3. And there's even more built on D3.js. There are these image specification languages, Vega and Vega Lite, and there's some Python libraries, Altair, Vincent, and D3PO that give you a Python interface to all these tools. Are you starting to get overwhelmed yet? You can link all these together. There's tools like Data Shader, which is kind of a bokeh tool that also works with Matplotlib. I'll show an example of that later. There's this thing called Viex, which is very similar to Data Shader that can render to all these 3 platforms. You have this tool Holoviews that links Data Shader and Bokeh and Matplotlib. And then there's this whole OpenGL cluster with Glumpy and VizPy. And there's graph visualizations, and there's all these ones that I don't even know how to categorize that deal with big data. So we just have this huge landscape of viz tools, right? And how do you make sense of this? Well, I'm hoping that this talk will help you make sense of this a little bit just by color coding these clusters, so that when you go out and you Google each of these later and check out the examples, you'll kind of know how they relate together. But for the rest of the talk, I want to dive into a few of these and show you some quick examples of what they look like, so you'll kind of have an idea of what you can do with them. So, of course, we feel like this. So how did we get here, right? It all goes back to Matplotlib. That's what I started with. And Matplotlib, for all the flack that it gets in the last few years, it really is a pretty incredible tool. Its strengths, it was designed to be basically just like MATLAB. And this was key to all the scientists and engineers who were transitioning to Python back 10, 15 years ago, you know, in the end of the 90s and into the 2000s. It has huge amount of rendering backends. You can, this is underappreciated. If you make a plot in Matplotlib, you can render it on almost any visualization backend. You can export PNG, PDF, EPS, SVG, all these different outputs. And that's not trivial to do, to make all of those different outputs look the same for the code that you write. And it really, it's powerful. It can reproduce just about any plot. It takes a little bit of effort to make most of these plots, even the most simple ones. And it's well tested. It has, this is almost a 13, 14-year history of Git commits. And it's really been battle tested and bomb-proof over the course of all that time. So Matplotlib, I wouldn't discount it. It's a really powerful tool. But you can do all these different things with it. But it does have its weaknesses, right? And if you've tried to do statistical visualization with Matplotlib, you run into this. So let's say you have some data, like this data frame of the iris data set, which you've probably run into if you've done any machine learning tutorials. You know, it's a relatively simple data set. And let's say you want to scatter petal length versus sepal length and color by species, right? You can say that in a sentence fragment. How many lines of Matplotlib does it take? Any guesses? This is kind of like the best way to do that, to scatter one variable by another variable and color it by a third. You have to do all this kind of boilerplate code. And the thing is that Matplotlib, as powerful as it is not very expressive in a lot of cases. So these are one of the weaknesses. The API can be pretty verbose. Sometimes the stylistic defaults are poor. You know, it was based on MATLAB circa 2001. So if you want plots that look like MATLAB circa 2001. But I should say that in Matplotlib 2.0 recently released, the stylistic defaults have been updated. So it's a lot better recently. It doesn't really support web or interactive graphics, which is what a lot of people want these days. And it can be slow for large data sets. So everyone's goal, the reason we have, in my mind, the reason we have this huge network of competing libraries is that everyone wants to improve on these weaknesses of Matplotlib, hopefully without sacrificing those strengths. And one way you improve on Matplotlib without sacrificing the strengths is you use Matplotlib. So all this kind of Matplotlib cluster here, what these tools have in common is that they are keeping Matplotlib at the core. So you have all those output backends, all that versatility, all that power, but you put a new API on top. So you address that weakness and you say, I can use Matplotlib, but I can make it easier to generate those plots. And the two that I want to highlight here are Pandas and Seaborn. These have been big in the PyData ecosystem recently. So Pandas, as you probably know, is a library that's meant to make data frames, store labeled data, labeled columns of data. And it has actually some built-in plotting functions. If you take any data frame like this iris handle and do .plot and then something else, there's all these different ways of plotting the data in there that are built in. So here we have, just in one line, we can scatter plot 2 columns of that data frame. You can even do more complex things. There are more sophisticated statistical visualizations in there. This is one that I discovered recently that I've never heard of before, but I think it's pretty cool. It's a way of taking all the columns of the data frame and turning them into a Fourier series and plotting them as lines so that each individual line is a row of the data frame. It's an object. And in some ways, those curves like encode the values in all the columns. So you can see just by looking at this that there are 3 very distinct types of objects in there, and you get a sense of the relationship. So these Andrews curves things are kind of fun. I'm looking forward to using them in my own work. So the other one I wanted to mention is Seaborn, and this is a library that was explicitly designed to make statistical visualization and more complex statistical visualization easy in Matplotlib. It wraps Matplotlib, it gives it a nice set of style defaults and color palettes, and you can do things in a few lines. It's kind of a higher level language, so you need to memorize more things. You don't have as many little composable chunks. But if you know what function you're looking for, you can do things in very short number of lines of code. So for example, you can call the pair plot function and get this pairwise comparison of all the columns in the entire data frame. So Seaborn is really, really nice if you want to do statistical data exploration in Python using Matplotlib. Okay, so then there's this JavaScript cluster, right? And the reason everyone loves JavaScript is because it's the lingua franca of the web these days, right? So you can do incredible things in JavaScript because it brings that interactivity to your browser, and everybody has a browser, right? You don't have to worry anymore about these cross-platform rendering backends. You just render to the browser, and the browser developers have taken care of all the hard parts. So the common idea here is that you basically build an API in Python that generates some sort of serialization of the plot that can then be passed over to the browser. And inside the browser, you have a corresponding JavaScript library that reads that serialization and renders the plot. That's kind of what every one of these tools does in some manner or another. And I want to focus real quick here on Plotly and Bokeh, which I think are the most developed of this cluster of tools. And they're both really nice. They give you this interactive feel that's really missing from Matplotlib. So this is plotting with Bokeh. The same data, I'm just taking the columns and doing a circle plot and then showing it, and you have all this interactivity. You can click and you can zoom and you can pan around. And if you go a little deeper, you can start doing things like adding controllers, and you can add tooltips to the points and things like that. Bokeh is this really incredible language that lets you do these sorts of visualizations. If you look at the gallery of Bokeh, you go online to bokeh.pydata.org, and you can click on each one of these, and since it's browser-based, each one of these examples in the browser is interactive, and you can start clicking and dragging and get a feel for how it works. So Bokeh is out of Continuum.io, the people who brought you Anaconda and Numba and some of these other great tools. So I'd really suggest taking a look at this. Like I said, advantages, you have this interactivity, you have several different layers and different APIs for generating things. The disadvantage is you don't have the same array of outputs that Matplotlib has. So at the moment, unless I'm mistaken, you still can't do PDF or EPS outputs. And so if you're a scientist who was writing a paper for a journal that requires PDF or vector-based graphics, you're out of luck. And it's also a slightly newer tool. It doesn't have as much of a user base. It's not as battle-tested as Matplotlib, but it's really getting there. It's an awesome program. So Plotly is quite similar. The story with Plotly is it's actually a startup out of Montreal, and they have this interesting kind of like open source / closed source model where a whole lot of the Plotly tool is open source. BSD license, you can use it for whatever you want, but there are a few features that they use to kind of make their money, and they charge you if you want a little bit more. And that tends to be things like automatically hosting the plots on a website with some sort of server backend, that sort of stuff. But I know a lot of people who are using Plotly, the free version of Plotly, for some very nice visualizations and for even scientific visualization, and they can do all sorts of different things. They have some things that Bokeh doesn't, like 3D plotting and animations built in. I might be wrong there. I think you can do animations in Bokeh, but it's not quite as easy as Plotly. But it's very, very nice visualization framework. And the cool thing here is it's not only a Python library, it's also an R library, it's a Julia library. They have these different ways to target the JavaScript backend from different languages. So like I said, the advantages are similar to Bokeh. It has all this web view interactivity, it's multi-language support, it has 3D plotting. Some features require a paid plan, and depending on your kind of software philosophy, that may or may not be a turnoff to you. I know some people who go either way on that. But I think it's a great library, and I would suggest checking it out if you're interested in these interactive visualizations. So the next thing that comes up, Matplotlib is not very good for these visualizations of larger data. And there's a bunch of these libraries that address that deficiency of Matplotlib. And they do things like relying on OpenGL, this VisPy and Glumpy right there. Glumpy or Glumpy, I don't know how to pronounce it. The things like Datashader and Viex, these are interesting ones that actually use really efficient code so that rather than delivering data points to the GPU or to the computer to render, they pre-aggregate all the data and deliver pixel, basically bitmaps, to the computer to render. And so when you have 1 billion points, there's no point in sending 1 billion points to your visualization screen because there's not 1 billion pixels to work with, right? So you can pre-aggregate those and do kind of heat maps, and that's the strategy these use. And then these other tools down here are really nice. I wish I had time to go into them. A few of them come out of the astronomy community for visualizing large three-dimensional data sets. So if you're interested in that, check out the gray zone down in the left corner. But I want to take a look really quick at Data Shader, because I think this is a nice project. It's still in pretty active development, but there's some impressive demos. And I have to apologize. My plan was to do a live demo of Data Shader because I think it's so awesome. But then all of a sudden I had a kid in the keynote, and it didn't really happen. So I have screenshots. So yeah, Data Shader, what it allows you to do is these fast server-side things. So it's a fast server-side engine that does dynamic data aggregation. So you can take things like the census data, where you have 200, 300 million points, and in real time you can visualize those on a map. And the live demo I could do here is you zoom in and out, and in real time it's actually calculating the bounds that you're looking at, figuring out what subset of the data matches that, and then re-aggregating it and sending it to the screen. So if you want to work with hundreds of millions or billions of points, Data Shader is awesome. So this is a zoomed-in view. You can smoothly zoom in on Lake Michigan and Chicago and get a more detailed view of the points inside there. So, and you zoom in even farther and you see kind of like neighborhood level data. So I would really suggest playing with this if you want to visualize really large data sets. You can go and download their demo notebooks. The installation instructions are pretty easy, and it's a fun package. So another class of algorithms here that I think is really interesting is the ones that start to tie these all together, and in particular, Holoviews up there, and then Altair down in the bottom right. These are like new kind of declarative language specifications that target different backends within the system. They might target Bokeh or Matplotlib or D3. And they let you create plots in a very expressive way and in a very powerful way. So the first one is Holoviews, and this is a really interesting project. It's worth watching. I first heard about it a couple of years ago when they gave a demo at the SciPy conference. And the initial philosophy of this was that data sets should have kind of intrinsic to each data set is the best way to visualize it, right? So if you have a data set consisting of columns of certain numbers, there is an intrinsic way that it should be visualized, and we as programmers shouldn't have to like think about that and twiddle the x-axis and the y-axis and the labels and the ticks and the colors. The computer should just know how to visualize this data. So what Holoviews started as is a way to wrap data sets in an object that when you eval or when you do a representation of that object in the notebook, it gives you the visualization. So rather than saying like, this is a data frame, it's such and such address, it actually gives you a picture of the data. And they've built in all sorts of really, really interesting interactivity on top of that. And you can do things like map data. And from what I've heard, I was talking to some of the Bokeh developers, it sounds like Holoviews is going to be kind of wrapped into Bokeh and is going to become their sort of declarative layer for visualization within Bokeh. But Holoviews also, you can see the links I put here. It also can target Matplotlib, it can target Data Shader. It sort of works seamlessly with all of those tools. So no matter what backend you need, if you need an interactive backend, if you need a big data backend, or if you need a backend that can output every plot file or a figure file imaginable, you can use the same system. So I think that's a really powerful way of going about it. The last project that I want to talk about is kind of my pet project that I've been working on for a little while. It's this library called Altair. And the idea here is that what if instead of passing around pixels, we actually pass around the data itself with the metadata that describes what kind of plot that we want. This is something that's been really exciting. The underlying library underneath Altair is called Vega and Vega Lite, and this has been starting to be adopted by things like Wikipedia and saying, you know, we don't want to just save a bitmap. We want to save the data, and we want to save the specification that tells the web page how to visualize that data. And I think this is a really powerful idea because if it can be adopted widely, we'll be able to use all that whole ecosystem of tools and say have Bokeh output a Vega Lite specification that could then be read in by Matplotlib and could be passed on to something else. And I've been talking with academic journals in the astronomy community about the possibility of having scientists submit their figures in the form of these sort of specifications, so that then the journal could generate a PDF to be printed, but it could also generate an interactive plot, equivalent interactive plot to be on their web page. So I really think this is the future, and this is kind of my soapbox that I'm pushing. But so what we're pushing here is this idea of declarative visualization, and this is a project that's in collaboration with my colleagues at the eScience Institute, at the Jupyter Project, and also the Interactive Data Lab at UW, which is the people behind tools like D3, which you might know about. So what's the difference between declarative and imperative? Well, imperative visualization, think Matplotlib, right? You can say in one sentence what you want the plot to be, and then you write 50 lines of code to make it happen, right? Declarative visualization is trying to make the code as close to that as close to that one sentence description as possible. You say, I want X to be this variable, Y to be that variable, and color to be this variable, and show me the result. Right, so imperative, you're specifying how something should be done, all the little steps, all the manual plotting steps, and the specification and the execution are kind of intertwined. In declarative visualization, you specify what should be done, and the details should be determined automatically by the system. This is quite similar to if you're used to database languages, like the difference between doing things by writing a Python script to sift through data and writing a SQL query. The SQL query is a declarative specification of what you want the system to do, and the system can find the most efficient path to doing that. So the key here is that this lets you think about data and relationships rather than these incidental details. And Brian Granger, who's one of the IPython developers, actually used this library, Altair, to teach an intro data science class this last semester, and he's really excited about moving forward with that. So I think what we're trying to do is free students to start thinking about relationships and data rather than thinking about syntax and libraries. So where does this come from? You've probably seen the D3 language. I'm gonna click over here and go to the live version. If you go to the New York Times and see any of these really interesting interactive demos where like you hover and you see different things, basically anything at the New York Times that looks like this is written in D3. And that's because the New York Times graphics editor is Mike Bostock, who wrote D3, right? So he uses it a lot. And he makes all his people use it a lot. And I just killed my full screen. How do I get it back? Yeah. So D3 is super powerful, and you can do these amazing interactive graphics, right? But if you've ever tried to use D3, you figure out that it's so ridiculously low level that unless you're Mike Bostock, you can't do anything with it. Right, so here's the example. This is literally like the example from the D3 example page of how to do a bar chart, right? like, okay, I'm gonna do a histogram to see. This makes you wish for Matplotlib, which is, it's crazy. But so after Bostock went to the New York Times, his advisor Jeff Hare, who was down at Stanford and helped develop D3, moved to University of Washington. Yes, and he thought about this and said, we need a better way for actual scientists and statisticians to visualize their data. So they wrote this specification language called Vega. And Vega improves on this a little bit. It's no longer this imperative list of commands for creating axes and things like that. It's a declarative specification that says, this is my data, this is what I want linked to the x-axis and the y-axis and things like that. But it's powerful. Still, you're not going to like sit down and write this JSON structure to see a bar chart of some data you're exploring, right? So once they got Vega working, that's this powerful, powerful thing that's underlying a lot. They said, we need it to be simpler. So they made Vega Lite, right? And Vega Lite this is almost getting to the point where you could just sit down and type this in a text editor and make it happen, right? You're basically saying, these are my data. I want a bar marking, and I want the x to be A and the y to be B, and it spits out that output. So what we're doing in Altair, what the Altair library does fundamentally is it's a Python API that creates these outputs. It creates these JSON specifications. Because I like writing Python, I don't like writing JSON by itself. So Altair, this is what it looks like. You have the data in a data frame, and you say, I want a chart with that data, I want a mark bar, and I want x to be A and y to be B. Right? So all of a sudden, you're literally just telling the computer what you want to be shown, and the computer figures out how to display it. And the output of this code is basically exactly this little JSON object. And now you can start passing that around to other libraries and other places. And so you've separated the specification of the plot from the execution of the plot. And I really think I'm hopeful for this as a model moving forward for interoperability between all these Python libraries and also between libraries in other languages, in R and Julia. So here's another more complicated example, going back to our original plot that we did in Matplotlib. We want to say that x is the petal length, y is sepal width, and color is the species. And you just write that out, and you can start adding things like the opacity of the circle. And if you do this to a dictionary, which is Python's basically JSON representation, you get a dictionary that describes the plot. That's everything you need to know about the plot in order to recreate that. So this is really fun, and you can do some incredibly powerful things with Altair. These are some of the more advanced examples that we have for doing different types of data visualization. I especially like this. Does anyone recognize this kind of yellow and blue plot in the left middle? That's the plot of measles incidents over the course of time. And there's this cutoff right there, and that's when the measles vaccine was introduced. So you can see in the historical data, each row is a state, and each box is a year of number of people who had measles. And you can see the effect of this vaccine. It just works really well. So you can check that out. Go to Altair, I think it's altairviz.github.io, and see that. And I should say that this is under pretty active development. One thing that has just happened is Altair 2.0, or Vega Lite 2.0 has come out. And this is incredibly exciting. The grammar of visualization, is not a new thing. Other people have done that before, but what they just added is a grammar of interaction. So you can build up these little these interactions from basic building blocks. And we don't have that in Altair yet, but my project for June, as soon as I'm finished with parental leave, is to finish this and get Altair out there so that you can start doing interactive declarative plots. So anyway, this is how you can try it: conda install, pip install. You can get a tutorial. You can go to the website. And that's the visualization landscape. I have my contact info, but I'll leave that up there and take a couple questions. So thank you. Do we have time for questions? 2 minutes for questions. Yeah, 2 minutes for questions. Yeah, if someone would like to go up to the mics, we can do that. I can also talk to folks afterwards. Yeah. Oh, we got a Bokeh developer coming up. Uh-oh.
My last commit to Bokeh, I committed directly to master, an example, and I broke master with my example. So
okay.
I don't commit to Bokeh anymore. But I have a statement in the form of a question. But first, I want to thank you very much for this comprehensive. This is not an easy thing to put together, and thank you so much for doing the work here. But my question was, did you know that Bokeh actually also has an R interface? So it is also.
Yes, I did know that. I should have mentioned that.
But thank you, Jake, for a great presentation.
Mm-hmm. That was phrased as a question. That was really good.
Thank you very much for putting this together.
Yeah.
Regarding Altair, I'm very interested, but I invested like a few years of my life a little while ago in learning ggplot2. I'm just wondering, when you were looking at your grammar, have you looked at things like ggplot2, which were very successful using the grammar of graphics of others?
Yeah.
I'm hoping your API is influenced by them so that I won't have done all that work for nothing in the past.
Yeah. So it's quite similar, and our API in Altair is really influenced not as much by any of that work, but by the Vegalite specification itself. Like our API is 95% of it is automatically generated by just reading the Vegalite schema and creating a Python object hierarchy, and then a few little bells and whistles on top of that. And one of the things, I didn't put this slide in, but one of the things I'm most proud of is we have two-way back and forth, or actually three-way conversions. So I can take Altair code and generate Vegalite specs, and then go from Vegalite specs back to the Altair code. So I can do this round trip thing, and literally our unit test suite that tests every conceivable thing is like 12 lines of code that just does this round trip on all the Vegalite examples. I thought, I was totally geeking out about that. I was smiling for like 3 days. Yeah. Thanks.
I happen to use the Vegalite before, so since the Altair provides the Python API, does that mean that I still need the web browser to see the graphics?
Yeah, you need the web browser to see it because it's a JavaScript library that finally renders the graphics. That's not a fundamental limitation. There's work on creating a Vegalite renderer in Matplotlib, for example. But right now we have it tied to the Jupyter project and Jupyter Lab, and it's kind of seamless. You just create the Vegalite object, and Jupyter knows how to render it in the browser.
Okay. Thanks.
Okay, maybe one more question.
Yeah, I guess
Can
mine
I-
would be the last question. So the question is, how do you solve for the I/O problem? Because it looks like the billion data set that you're showing, was it in memory? If it is in memory, like, how do you get into the memory from database?
So this is a question about data shader. Actually, I'm gonna defer that to people like Peter, who asked the first question, because they can answer a little bit more about data shader and some of those things going on. I'll take one last question.
I can take it offline if we need to wrap this up.
Is it a quick one?
Moderate. Yeah, I think so, right? So as far as interactive graphs, you showed a lot of options there, but mostly it's centered around zooming and zooming and geographical constraints. What about slicing data? Say, for instance, the census by income or race, which would require some user boxes.
Yeah.
Are any of these tools set up for that, or do you have to pass it a different JSON?
They are, yeah. If you look at the Bokeh project in particular, they have this way of creating dashboards that are really, really powerful. They can either be client-side or server-side dashboards. And if you look at the Bokeh examples of all of those, there are examples of using sliders in conjunction with visualizations and things like that. So I'd check out Bokeh for that.
Cool, thanks.
And we're hoping to get there with Altair too. So thanks very much, everyone.